Imagine a box in the middle of an abyss. The box is a good conducting domain surrounded by a bad conducting domain. An electron would obviously rather be inside the box than outside it. The box is now what we call a quantum dot, a nanoscale well-conducting low-energy domain with a countable number of electrons within it surrounded by a bad-conducting high-energy domain. So quantum mechanics says that the electron inside the box also acts as a wave. The length of the electron wave would spread out to the length of the quantum dot. But why does this matter? Take this guitar. If we strike a longer string, we hear a low pitch, low frequency sound. But if we strike a shorter string, we hear a high pitch, high frequency sound. Similarly, when a smaller in diameter quantum dot is struck, it emits a high frequency photon, thus producing a cooler color. However, when we strike a larger in diameter quantum dot, it emits a low frequency photon, producing a warmer color. So here we see that if we take two quantum dots of the same atom and constellation but of different size, we get new colors and new properties. How do we even strike a quantum dot? In the Bohr model of an atom, an electron in a lower energy level will jump up to a higher energy level if we apply the right amount of energy. This is the process of absorption. The electron will eventually lose the energy and fall back to its initial state, emitting light, that is photon. This is called emission. So essentially, we're just trapping an electron and seeing how it responds to energy. Now, the energy of the emitted photon is the difference between the two energy levels. If we relate the wavelength of the photon to the energy levels using the Balmer-Rydberg equation, we can control the emitted light's color by calculating the energy difference. Quantum dots are being used to make fully emissive LED screens, quantum computers for encryption, solar cells, and even for tracking tumors.